Okay, let's look at how matrices and linear systems fit together. Here's the name of the generic, all the entry, here's the linear combination here. It's like the A11, A12. This is a linear combination of constants, the A's in the first row with the constants over here. This is the general pattern of a linear system. And if you notice, these A's then look like the entries of an n by n matrix, where the first row is the variables in the first linear combination, the second row is the variables, the second one, and then you have x1, x2, xn. And so I'm going to make a column vector of the variables and call that x. So we have an n by 1 matrix, x1, x2, x3, x4, x5, which we can think of as a vector. Now, when it's thought of as a vector, you call these entries components. So that's a sort of a verbal change so they came from different origins historically. Okay, so you have this, and then I can take the matrix of coefficients of this system, where I just list all these matrices, all the numbers here. Oh, and there's a typo here. These x's shouldn't be there. Okay, that's an error in the text. And I carry it along. Can't believe that. Okay. Anyway, well, so much for that. And then so I extract from this the vector of the variables and the matrix of the coefficients, and if I multiply them, it's a general times a column matrix. I get up the vector with all the linear combinations in a row. So if I make the vector of the constants be here, I can write my linear system as a matrix equation. Now, this is not the augmented matrix. Let's do an example to see how this works, because this is something a little different. Let's say I have the linear system 3 times x plus 4 times y equals 7, and 5 times x plus 9 times y equals 8. So the problem is, write down the matrix equation for this linear system.
Sorry, but is it 3x plus what y?
3x plus 4y.
4y.
Yeah. And this is 9y. When you're finished, raise your hand. Okay, now if you wrote down this is wrong. This is the augmented matrix. It's not the matrix equation. What you want to write down here is the matrix of coefficients, 3, 4, 5, 9. It is the thing that appears over here, times the vector of the variables, right, x, y, equals the vector of constants. This is the matrix equation of linear system. It's another representation of the linear system in terms of matrices and vectors. It's the same information. Now, if we carried out, just to check this, we can carry out the matrix multiplication here, right? A 2 by 2 times a 2 by 2 times a 2 by 1 is going to be this matrix here is going to be a 2 by 1. What's 3 times x plus 4 times y and 5 times x plus 9 times y. The same rule of matrix multiplication. And if that's equal 7 and 8, now these are equal, these two vectors are equal, matrices are equal exactly when this entry equals this entry equals this entry. Well, those two equations are 3x plus 4y equals 7 and 5x plus 9y equals 8. So they're the same thing. You have a linear system as a list of equations, and the equivalent linear system as a matrix equation. In either case, for both of these, we would form the augmented matrix. So the augmented matrix here, you can see, is a combination of the coefficient matrix in this column vector here. And the same thing when you extracted that from the linear system. Okay, so that's the connection. Now it turns out that there's a third form. Let's look at this one. Let's look. Okay, so this form here is equal to this, right? This was this intermediate one when I multiplied in, and then I went here to this, but I could also do the following. I could say, well, this is the sum of two vectors, right? 3x, 5x plus 4y, 9y equals 7, 8, right? See, I sort of, this is a sum of the x terms, y terms, so I could separate, I could undo this vector with this matrix sum by decomposing it this way, right? Then I can, for the first one, factor out the x to write x times 3, 5 plus y times 4, 9 equals 7, 8. So this is the vector form, right? Of linear system. And this is the form that we'll use going forward into vector spaces. It's like somehow it's saying this linear combination of vectors, you know, instead of, you sort of have and this looks a lot like our solution set, right? It looks like how we were writing our solutions. So this is a third form that comes from the same matrix operations as this one. So that is behind this whole thing here. What you need to do is be able to translate from system to equation and back again. And then you can also check, for example, one of the things that enables you to do is to check. If we want to know, let's say I had this x, y equals let's say that here's a matrix equation. The question is, how do you determine is 1, 1 a solution? In other words, is this a solution of the linear system here written as a vector? So what you can do is you would just plug in the 1, 1 here and do the check 1, 1 and make this product, and the answer would be 1 times 1 plus 2 times 1 is 3, and 3 times 1 plus 4 times 1 is 7. And then you can check, well, 1, 2 is not, this is a solution, because you could check it, and this is not a solution, because you could check 1, 2, 3, 4, 1, 2, which equals 1 times 1 plus 2 times 2, that's 4 plus 1 is 5, and 1 times 3 plus 2 times 2 fours is 8, 11, and this is not equal to this one, whereas these are equal. So that's one way to use the matrix equation to answer a question. That's the second part here.
So we did 1, 1, and
You just you say, is this a solution? You just plugged it into the matrix equation here, did the product, and then compared this product with the right-hand side. In this first case, they were equal, but in the second case, they weren't equal.
okay, so the 1, 2 is another.
So 1, 2 is not a solution, and 1, 1 is a solution. And you can see that. So it might be that you have an infinite number of solutions, right? So it could be that this linear system has an infinite number of solutions. So I could give you 3 things here that are all different, but all solutions.
I would,
This one doesn't. This one probably is a linear system with only one solution. So it probably, for this case, that's not the case.
okay.
But for other systems, other linear systems that do have a free variable, they might have an infinite number of solutions. And here's how you can check that. Okay, I think that's basically what you can do with this form.